Okay, thank you for the invitation today. Yeah, I have used Yosys in a few passes for this work. So this is a work that we presented at the CCS conference last week or 2 weeks ago. And it's called MicroCFI, Formal Verification of Microarchitectural Control Flow Integrity. And I've done it together with my colleague and the professor here at ETH Zürich in the computer security group, ComSec. So CPUs are usually verified via testing or fuzzing, but that's a method that is not complete. So you rarely simulate all possible programs. For security, we need to be sure that there are no more bugs in a CPU design. And formal verification is one method that can give us these guarantees. However, it's often perceived as very complicated, and it's often a CPU-specific and a manual effort. In this talk, I'll present you microCFI, a generalized security property that can be easily applied and reused on different CPUs and can be used independent of the CPU's verification state. And this one property can capture multiple threat models. So let me first define the microarchitectural control flow. We define it as the program counter values and update time. So it's the clock cycle accurate values of the program counter in a CPU. What could go wrong with this microarchitectural control flow? Let us look here at a program that is constant time on architectural view. So we have here 5 RISC-V instructions, where one of them reads secret data, the add-I. But usually these instructions are, at least this add-I is executed in constant time, because most of the time, it's only multiplication or so, which have data-dependent execution time. So for example, we execute it on some imaginary CPU with operand value 0, and it takes 5 clock cycles to execute all these 5 instructions. However, it's possible that there are CPU bugs. So for example, it could be that the add-I now, depending on the operand value, changes the behavior either of itself or of another instruction, and therefore executes in different amount of time, and also therefore updates the PC, the program counter, a clock cycle later. So this data dependency and this data-dependent time leaks the data, leaks the operand, and basically this creates a timing side channel. Now let's look at a second problem. Here we have a program that looks on architectural or software view completely fine. It does have an exception at the end, but then it goes to the pre-programmed exception handler. Everything good. Now imagine this add-I now reads input data. Input data could be potentially attacker controlled. If there is a bug in the CPU, it's possible that this input data ends up in some internal buffer and then changes the program counter. And if such a CPU bug happens, then we have a possibility of a control flow hijack. With microCFI, we aim to detect such cases. So we want to prove that there are only ISO-specified control and data flows from instructions operand to the program counter, and detect these non-ISO specified flows. And this one property can capture both of the threat models that I've just discussed. That is, if we interpret the operand as a secret, then if it flows to the program counter, there is a timing side channel or an information leakage happening. But if we interpret the same operand as attacker controlled and it can change the value of the program counter, then a control flow hijack attack is possible. And these properties are information flow properties. So there is an information flow property, you always have a source and a sink, and you specify that there should be no information flow from source to sink. So in our case, that would be the operand and the program counter. And information captures everything. It captures the value updates, and it captures the time update, and also the control flows. So if the operand influences one of these two, either the data flow or the time or control flow, then there is one of these two attack possibilities happening. And that's why we want to find such kind of bugs in a CPU. And what we do to be able to track such information, we use a taint logic called cell lift that has been developed by my colleague Flavian Solt earlier. That's already open sourced. Here's the link. And this taint logic is a Yosys pass. It instruments the design with the taint logic, and the taint represents then the secret or attacker-controlled information that we want to track through the design. So a quick introduction how it works. We take the HDL design and then we load it into Yosys to get the RTL-IL, the intermediate representation that you all know. And then we iterate through all the cells, duplicate basically the inputs and outputs, and create a taint signal. For each signal bit, you get a taint signal bit in the shadow logic. And then for each cell type, we have a specific rule. And based on that rule, a taint logic is generated. And this taint logic then runs in parallel to the HDL, so that's only used for verifications. We don't implement it in a design or anything. And with that, we can then specify properties over it. So here I can quickly recap how it works. If we have, for example, an and we have one input tainted and the other input 0, then the output of this AND will always be 0. So here the tainted input cannot change the output, and therefore there is no information flow. On the other hand, if we have an and the one input is 1, then the output of the AND only depends on the tainted value. And as if that's, for example, a secret, then the secret would leak via this information flow, because then we can observe it if we observe the AND's output. So using this taint logic now, we can specify formal properties over it. We use system Verilog assertions, and then put it in a model checker and get either a proof or a counterexample, depending on whether the property was violated or not. The other way around. So let us look how this works inside a CPU. Here we depict how taint enters. Taint enters in RISC-V always via registers. At least in our model, we injected in the registers because every instruction operates on register data. And then taint propagates somewhere through some buffers in the CPU, and we check whether it ever flows to the program counter. So if here we have an add and we don't see any flow. But what if we take a branch? The branch has obviously changed the PC, so we do see a flow. But is micro-CFI violated? Not necessarily. Branches, at least direct branches, are expected to change the program counter in certain ways. But the point is that they are only expected to change the program counter via control paths. So for example, here in this if, the operands, which would be, for example, a secret, they are allowed to choose between one of the two branch targets, but it should not be possible that this operand value directly flows into the PC and directly changes the program counter. That's only in an indirect branch, which we are not checking because indirect branches are expected to change program counter. So we only look for flows that are not expected. Thus, these control flows, they are also expected, so we don't want to flag them as errors. And to do that, we have developed cell DFT, which is a variant of cell lift that only tracks data flows. I will explain this now a bit more in detail, how it works. So cell lift, like we said, cell lift tracks all data flow, all information flow, all timing control, and it's bit accurate. That's the same for cell DFT. But what cell lift does, for example, here, if we have the multiplexer select, which is a control signal, if we have this tainted, then the taint flows to the program counter eventually. So this control of the program counter via the multiplexer select is detected by cell lift. That's how it should be, but that's not violating micro-CFI. So with cell DFT, we block these kind of flows. So basically it's all the same cell lift rules, but then some rules are modified so that the taint propagation of controlled paths within cells is blocked. So in the paper we have the details, and here also quickly depicted. We block basically all the control flows. Here there are some cells, for example, comparison reduction, where we also block the taint flow. This has the assumption that they are not used in the data path. This could be too strict, so we could actually think of implementing a second version where we only block the taint flow via the control, for example, of enables of flip-flops or of the select of multiplexers. But currently we also block these flows where, for example, a reduction to 0 happens, so where the data is reduced to a Boolean value. And then if we use this cell DFT, now a branch would not anymore cause a violation. Now let us look how we verify multiple instructions. Here we have an add-I and a CSR write, and we see a flow to the program counter. How do we know now which instruction has caused this problem, or if it's a problem? We could, for example, check after each instruction whether the taint reached the PC. Then now after the add-I, we would conclude that there is no flow. Then we execute a CSR write and we see a flow. The question is, was it the CSR write that caused this flow, and was it a problem? Because in fact, in RISC-V, CSR read write is expected to change the program counter, and therefore this flow, if it would come from the CSR write, it would not be a problem. We would actually not even consider it as a bug. So we would miss this kind of example that we had in the beginning, where actually the add-I's operand was changing the CSR write's behavior. So this interaction between instructions is important to consider to find these very subtle bugs. What we want is that we can achieve security classification for each instruction type, so that we can communicate this to software, and then you know, if you write the program in constant time on software level, which instructions you can use. And we want to have these guarantees not only for the instruction in isolation, but embedded in any possible program, because formal verification verifies all possible programs. We can achieve this if we take care of certain things that I'll tell soon. And we also want to be able to know which of the instructions in a sequence has caused a leakage. If you have, for example, 2 add-I's, this is just to make the debugging simpler. We want to know which of them has caused the problem, because in verification, you know, you spend about 50% of your time debugging. So now we want to have very precise counterexamples. And of course, we want to not limit our security guarantees. So we want to see all influences on other instructions in future for any infinitely long programs. So to achieve this, we use precise taint injection. We now go into how the formal setup works. So we abstract the taint logic from the register, and then we control it with assumptions, which is constraints in the formal setup. And we control them with taint injection conditions, where we make sure that only one instruction at a time reads tainted data. And in the paper, we have the proof that the way how we write our properties and assumptions, we have to guarantee that every instruction at every possible position is considered. And these reading conditions, these taint conditions, we generate with a Yosys pass. So now I'll go a bit more into detail on how this one works. The pass is called update condition, and it has 2 modes. One is the read from condition. That is a condition where we read the signal value of one signal from a chosen other signal. So here we want to read the operand from the register. So we give the operand signal's name and the register file name into the Yosys pass, and then we get the condition when new data is taken from the register. Doesn't mean that this data has to be actually have changed, but it's whenever the data operand signal is updated with the new data, or even if the value has not changed, but it could be, for example, that an instruction wrote back the same value to that register, and then we want still to know that now it's basically a fresh value. This pass takes the design, and then it finds this condition in which the operand reads. So here I took the PIC-ORV 32, and this is the operand signal, and it reads from the CPU register when decoded RS1 is true. And this same condition is what then the pass in the end gives out. So it extracts this condition. And that allows us to read in the same condition like this CPU reads from the register. And therefore we don't have to care if the CPU has been already verified or not, because we use exactly the same condition. Whenever data enters in the CPU, we also track it. For sampling the instruction word, we use the same pass. So there we check when is the register address read from the instruction word. And then in our test bench, we also sample in the same condition. And so to check when taint should be injected, we check for the instruction word type and the taint start condition. Then for the update, for the taint stop condition, we have a condition that's called update condition, and that is the condition whenever the signal gets a new value, or it doesn't have to be a new value, but at least it could be a new value, and when it reads it from somewhere else than its own previous value. So if we think of a flip-flop with an enable, it's whenever the enable condition is true, whenever new data could enter. Or for continuous assignments, it's simply always true. So whenever this update condition is true, then we stop the taint. And the properties are written in a way so that we could have potentially multiple taint injection windows per instruction. So whenever there is data entering, we start tracking, and we stop when it finally ends and the instruction has changed. And by that, we can then associate any property violation to exactly a specific instruction. To go a bit into the path, how it works, we call it with some signal, and then it's basically called recursively. So it's called, in case of the signal is assigned with some value, then we call it for the other side of the assignment. If it's done with a flip-flop, then we have to add a past attribute. We do this with the Yosys source attribute, and then later this is translated into a system Verilog past system function. If it's assigned with a multiplexer, then we take the update condition of one of the inputs whenever the respective condition is true. If it's a flip-flop, then we take again the past, we add the past, and take the enable condition. When the enable condition is true, we call the update condition of the input to the flip-flop. And for everything else, we return a 1. And if it's the signal itself or it's already visited, so to avoid loops, then we return a 0. So that means that in the end, what we extract is these conditions when it reads from somewhere else, but not from itself. And for the read from condition, it's almost the same, except that now we want to read from a specific signal. So we return a 0 for all these other things, like a constant, like input and so on. And only when we find a signal that is the one that we put in as input, as the chosen read from signal, then we return a 1, and then we get exactly the condition when one signal is reading from another one. And this we create also on the cell level. And then we get this output. If we translate it back to HDL, that's how we currently do it. And then we could also already use this signal in our formal setup, but for better readability and better debuggability and also portability of the conditions, we have a Python script that reconstructs these conditions back into the original design signal names and also into a shorter form. So basically it replaces all of these outputs, all of these generated intermediate signals step by step to get back to a design-like condition, which is simplified and better readable. There is one more thing we have to take care of. So now we took care of precise taint injection, but we also need to take care of this communication between instructions. So of course, if we have one add that writes to a register T1, and then we have a branch following that reads from T1, there is an information flow through that architectural register. But this information flow is not a problem that we want to detect. So we already know if the add writes to the register and the branch follows, then of course the branch accesses this. So if you would do that on software level, then you would actually violate the constant time principle already on software level. So in order to not flag this as a violation of our property, we block the paths through these architecturally known signals and ensure that we not block any other internal paths. These are the ones that we want to detect if they exist. And at the same time, we need to be sure that we also track data that comes into the instruction via the forwarding path, or at least in the condition when forwarding happens, because it's possible, due to some bug, it would be possible that taint flows only in case of data was received via the forwarding path, and also those kind of bugs we would want to detect. And to achieve this, we find these multiplexers that choose between the register data and the forwarded data, use a logic abstraction on the select of the multiplexer, and that then allows the taint to propagate from the register, even in the forwarding case. And these multiplexers we find also with a Yosys pass. And also we have in the paper a so-called declassification precondition, where this one has to be fulfilled so that the declassification does not block too much information flows. Like I showed before, we don't want to block unexpected flows. And this basically checks that all the outgoing parts of a signal that we declassify means we set the taint to 0. So all outgoing parts of these signals should not reach the program counter without either passing through another declassified signal or another forwarding multiplexer. And this condition is checked in this pass, so that's all done at once. We start with the forwarding output signal. Then we see if we have on all the paths, on all the outgoing paths, we do check the condition. And then if we find a multiplexer, we go back on the other input of the multiplexer and see whether this one goes to the register. If it doesn't, then it's not a forwarding multiplexer, then we just continue like all the paths and check that the condition is fulfilled. And if we find a multiplexer where the other side, the other input goes to the operand register, then this is a forwarding multiplexer, and then this path returns you these select signals that we then in the formal setup abstract and therefore have this taint injection also via the forwarding path. And we have verified with this method 4 RISC-V CPUs. One was the Pico RV32. Then there was also the EBEX that's used in the OpenTitan root of trust. They are all in-order CPUs, microcontroller class. It did not scale that well, so that's why we stayed with the small CPUs. But we also didn't implement any specific measures for scalability. And for SCARF, we also looked into the crypto extension and the crypto instructions. Still, all of the instructions could be proven in less than 24 hours. We used the Cadence Jasper Gold model checker here. We have written it in system Verilog assertions, but it could also be written in just simpler assertions. And we proved a lot of instructions, also all the crypto instructions for SCARF, and also found some violations on all of them, but some, for example, in Pico, they were documented and fine. But we also found some security vulnerabilities that were not yet known. For example, in the Kronos CPU, we had this running example that I had throughout the presentation. We found this in Kronos and also 2 other control flow hijacks in Kronos. In EVEX, we also found a constant time violation that also led to a data leakage. And for these, we got some CVEs and also a control flow hijack, but in some custom configuration. So now I've introduced you a generalized CPU security property, micro-CFI, microarchitectural control flow integrity. We have automated the verification method a lot with Yosys. The implementation is open source, and we have verified the 4 RISC-V CPUs that I've just discussed and have found 4 CVEs or 5 vulnerabilities. With that, I thank you for listening. Here we have the links to our group and to the GitHub where we have the code on all the Yosys passes and all the formal setup and so on. And thank you very much.
Thank you, Katharina. Yes, I see that people have already started raising their hands for questions. Joseph, go ahead.
Hey, I'm sorry, I meant to applaud.
No.
Thank you for the talk. I don't really have a question, to be honest. I just misclicked, but yeah, thank you.
Right. But then if other people have questions, please raise your hand.
Someone asked about the CVEs. I can go back again. So yeah, one was this one, where it was the add-I was passing the data. It was not only the add-I, so it was a few instructions that passed the data to a CSR write. So basically the CSR write was accessing data belonging to another instruction in certain cases when there were certain problems on the memory bus. And the same caused either a timing delay of the CSR write when it was affecting one of the performance counters in an overflow case, or it was affecting also one of the exception program counter registers, and then you could basically hijack the control flow in that sense that you could write into that exception program counter register and then change the program counter. And the other one, for EBEX, it was also triggered with a problem on the memory bus. And then this problem, so when there was, I think it was a load data coming in, but the EBEX didn't have set a load request before, then it would still react and its internal state machine of the multiplier got into some bad state. And then basically when you had another multiplication coming later, then it would not start in the reset state of the multiplication. And in the end, it would actually operate on the old data and transfer the value to the register. And the same problem also caused a problem with constant time when you had, so you had a sequence of instructions, and then EBEX has this constant time mode. So when you have switched on, it was all good. But then when you switch it off, and at the same time you had this error condition, then afterwards you had a timing leakage. So the constant time mode basically affected, when you switch it off, it was still the code that was executed before was affecting what happened after switching off. Otherwise, from my side, I say thank you for Yosys. It's a wonderful tool. We can do so many things with it. We have these 4 passes. Cell lift, cell DFT are quite generic, can be used for other things, for other kind of properties, have been used in other works, also for simulation. The update condition, if you have any ideas, I guess this can also be used for other projects. The last one that I explained with the forwarding multiplexes is very specific to our property.